Assalamualaikum. Hi, my name is Muhammad Irfan bin Zaifuddin, and today my group will present about machine learning in healthcare. And our group example of machine learning that is applicable in healthcare is for stroke prediction. Firstly, I am Muhammad Irfan bin Zaifuddin, and my two other partners' name is Muhammad Hazim bin Muhammad Razib and Muhammad Nur Akmal bin Ibrahim. For the introduction, by allowing the analysis of enormous amounts of clinical data, machine learning has completely changed the healthcare sector, improving patient care, reducing costs, and increasing operational effectiveness. With an emphasis on record management, predictive analytics, and robotics, we will examine the present applications of machine learning in healthcare in this introduction. These developments have altered how medical professionals identify and treat diseases, leading to more accurate and effective healthcare practices. So, there are three main parts that will be taken into account in this presentation. Firstly is for machine learning for managing records. Secondly, machine learning for predictive analytics on equipment and patient care. And lastly, machine learning for robotics in healthcare. So, for the machine learning for managing records, a large-scale clinical data management analysis heavily depend on machine learning. With the widespread adoption of electronic healthcare record, or EHRs, an immense amount of patient data has been produced. These records can be processed and analyzed effectively by machine learning algorithms, though yielding useful insights and patterns that may not be visible to human observers. So next, for machine learning in predictive analytics on equipment, algorithm for machine learning can be used to anticipate equipment breakdowns or malfunctions and enabling preventive maintenance and minimizing the downtime for the equipment. Algorithms of the machine learning can analyze sensor data from medical devices and equipment to find patterns that point to possible problems and therefore enable a quick response. Next, for the machine learning in predictive analysis on patient care. So in order to foresee illness development, risk factors and treatment outcomes, machine learning models can analyze patient data, including clinical history, laboratory results, and genetic information. These predictive analytics have medical professionals make wise choices, customize treatment regimens, and predict potential risks. Lastly, for machine learning in robotics in healthcare. In healthcare robotics application, machine learning is essential by automating time-consuming administrative chores like monitoring patient records and arranging appointments. Robotic processes automation, or known as RPA, can free up the time of healthcare workers. Machine learning algorithms in surgical robots can improve surgical precision, enabling minimally invasive operations, therefore speeding up the patient recovery. So for our example of machine learning in healthcare is a stroke disease prediction. So for the data, we obtain it from the Kaggle machine learning website that provided this dataset. This dataset includes patient medical information as well as the outcome of the diagnosis of the stroke disease. Based on the medical data provided about the patient, machine learning models are required to assess whether a patient has a stroke disease and to expedite the diagnosis process. This presentation will also go into more depth about the factors that affect the patient's likelihood of developing a stroke disease. Next, for the problem statement of this presentation, is the problem at hand is to develop a machine learning models that using a dataset obtained from the Kaggle platform. This dataset consists of patient medical information, including various attributes, along with the outcome of the diagnosis of a stroke. The objective is to utilize this data to accurately predict whether a patient has a stroke disease, enabling a faster diagnosis process. Additionally, this presentation aims to explore and analyze the factors that influence a patient's likelihood of developing a stroke disease. Lastly, the solution for this presentation: when there is no access to the current medical equipment, early detection and prediction of stroke disease are more difficult. Many researchers and developers work to construct a stroke illness prediction model by employing various machine learning algorithms for the intervention of early therapy in order to address the issue. As an illustration, consider logistic regression, k-nearest neighbor, support vector machine, decision tree, random forest, and AdaBoost are all the machine learning models that will be used in this dataset.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Nur Akmal. Today I will present about purpose system of stroke. First is loading stroke dataset, and we go to data pre-processing, and go to cross validation and hyperparameter tuning. To that we have 4 classifier. First is logistic regression classifier. Second is decision tree. Third is support vector machine. And fourth is random forest classifier. And last we go to evaluating classifier. Model purpose about linear regression. Linear regression in a machine learning is a supervised learning algorithm used to model the relationship between input variable and a continuous target variable. It assumes a linear relationship between the variable and estimate coefficient to minimize the difference between predict and actual value. It is widely employed for tasks such as predicting housing price, analyzing trend in data, or identifying correlation between variables. K-nearest neighbor. The K-nearest neighbor (KNN) algorithm is a data classification method for estimating likelihood that a data point will become a member of one group or another based on what group the data point nearest to is belong to. The K-nearest neighbor algorithm is a type of supervised machine learning algorithm used to solve classification and regression problem. It's called a lazy learning algorithm or lazy learner because it doesn't perform any training when you supply the training data. Instead, it just stores the data during the training time and doesn't perform any calculation. This don't build a model until a query is performed on the dataset. This makes KNN ideal for data timing. Next is decision tree classifier. The decision tree classifier is supervised learning algorithm in machine learning that construct a tree-like model of decision and their possible outcome. This partition on the feeders space based on the value of input variable. Create a tree structure where its internal node represent a decision based on a specific feeders, and its leaf node represent a class label. It is widely used for classification tasks as it provides interpretable rules for decision making and can handle both categorical and numerical number. Next is random forest classifier. The random forest classifier is powerful ensemble learning algorithm in machine learning that combines multiple decision tree to make prediction. It constructs a multitude of decision tree and aggregate their prediction to obtain the final classification. Each decision tree is trained on a randomly sampled subset of the data and feeders, reducing the risk of overfitting and improving generalization. Random forest classifiers are known for their high accuracy, robustness to noise, and ability to handle large datasets with high dimension feeders, making them widely used for classification tasks in various domains. Next is AdaBoost. AdaBoost, short for additive boosting, is a popular boosting algorithm in machine learning that it literally combines weak classifier to create a stronger classifier. It's assigned weight to instance in the dataset, focus on misclassified one in each iteration, and adjust the weight based on their classification performance. This allows subsequent weak classifier to pay more attention to previously misclassified intents, resulting in an assembled model that improves its performance over iteration. AdaBoost is effective in handling complex classification problems and has been successfully applied in various domains, such as face detection and object recognition. Next is SVM. SVM is support vector machine. It's one of the most popular supervised learning algorithm, which is used for classification as well as regression problem. The goal of the SVM algorithm is to create the baseline or decision boundary that can segregate and dimensional space into class so that we can easily put the new data point in the correct category in the future. The best decision boundary is called a hyperplane. SVM choose the extreme point or vector that have in creating the hyperplane. These extreme cases are called as support vector, and hence algorithm is termed as support vector machine. And then we have attribute information. First is ID for unique identifier, gender for detect male, female or others, age for patient age, hypertension 0 if the patient don't have hypertension, and 1 if patient have hypertension. Hypertension is stroke, and heart disease 0 is the patient don't have any heart disease, and 1 for patient have heart disease. We have a type of work like children, government, neighbor work, private or self-employed. And then we have type of resident for rural or urban, and we have average glucose for detect level of glucose in blood. BMI we have for body mass index, and we have smoking status for formerly smoke, never smoke or smoke. Hyperparameter is model performance, functionality and structure are directly governed by hyperparameter. Data scientists may optimize model performance through hyperparameter adjustment. The effectiveness of this procedure depends on selecting the right hyperparameter value, which is a vital step in machine learning. Consider the situation when the model learning rate is being used a hyperparameter. If the value is excessively high, the model converts too rapidly and have unfavorable outcome, while training will take too long and the result might not converge if the pace was too slow. An accurate model and outstanding model performance are produced by a well-balanced selection of hyperparameter. Data and feeders about protocol. The straw prediction dataset was converted to pandas to facilitate data preparation, determine how the data appear to be cross-sectional either at a starting point or a specific time, performs a truth analysis of the data including a comparison of the study primary component and the data collected during its visit. We have 1022 patients aged 28 until 77 years. 967 patients were classified as not stroke, while 55 patients were classified as having stroke. Now about data preprocessing. First is data cleaning. This step involves handling missing value, outlier, and noise in the data. Missing value can be filled using technique like imputation, or row with missing value can be removed if they are insignificant in number. Outliers and noisy data can be identified using statistical method or domain knowledge and treat accordingly. Second is phaser selection. Identify the relevant phases that are useful for stroke prediction or analysis. Phaser selection technique such as correlation analysis of information gain can help determine which phasers contribute the most to the target variable. Phasers extraction technique like principal component analysis or linear discriminant analysis can be applied to reduce dimensionality if necessary. Third is normalizing or scaling. Normalize the numerical phasers to a common scale, which can help prevent one phasers from dominating others during the modeling process. Common scaling technique include min and max scaling or standardization. Fourth is encoding category variable. If the data contain category variable, They need to be encoded numerically for modeling purpose. One-hot encoding, label encoding, or ordinal encoding can be used depending on the nature of the category variable and the algorithm being employed. And last, feeder scaling. In some case, after splitting the data, it may be necessary to perform feeder scaling again on the training and testing set separately. This step helps ensure that the model is not biased by different in feeder scale between the set. It's important to note that the specific pre-processing step may vary depending on the nature of the stored dataset, the available feeders, and the requirement of the analysis or modeling task at hand.
Hello, Assalamualaikum. My name is Muhammad Hazim bin Muhammad Razib, and now I will present about improvement in the sustainability of machine learning. So first is model lifecycle management, implementing efficient model lifecycle management practice, including model pruning, retraining, and retirement, can improve sustainability. So continuously monitoring and optimizing models to ensure they remain accurate and relevant can reduce the need for frequent retraining, thereby saving computational resources. Second, training data optimization. Reducing the amount of training data required for machine learning models can contribute to sustainability. Techniques like transfer learning, data augmentation, and active learning can help minimize the need for large-scale data collection and labeling, thereby reducing energy consumption and environmental impact. Third is data center efficiency. Data centers that support machine learning workloads can be optimized for energy efficiency. This includes using advanced cooling techniques, efficient power management, and renewable energy source to power the infrastructure. Additionally, locating data centers in regions with cooler climates can reduce the energy needed for cooling. So next, I will present about environmental impact for the proposed solution. So first is energy consumption. While efforts are being made to develop energy efficient algorithms and hardware, machine learning still demands substantial computational power. Particularly for training large models, this high energy consumption can contribute to greenhouse gas emissions and increase the carbon footprint. It is crucial to continue improving energy efficiency and prioritize the use of renewable energy source to power machine learning infrastructure. Second, manufacturing and disposal of hardware. The advancement in machine learning often requires specialized hardware such as GPU and AI chips, which involve resource-intensive manufacturing process. This process can contribute to pollution, resource depletion, and environmental degradation. Additionally, improper disposal of hardware components can lead to electronic waste, which pose environmental risks. Implementing responsible manufacturing practice, promoting recycling and reuse of hardware, and designing modular systems can mitigate these impacts. Third is data center operations. Data centers that support machine learning operation consume significant amounts of energy for cooling, server maintenance, and data storage. Traditional data centers heavily reliant on fossil fuels can have a substantial carbon footprint. To minimize environmental impact, data centers can be optimized for energy efficiency, employ advanced cooling technologies, and transition to renewable energy source. Locating data center in region with cooler climates can also reduce the energy required for cooling. Future of machine learning in the design in medical device. So first is personalized diagnostic and treatment. Machine learning algorithms can analyze large amounts of patient data, including medical records, genetic information, imaging scans, and real-time sensor data. By leveraging this data, machine learning can assist in developing personalized diagnostic and treatment plans tailored to individual patients. It can help identify patterns, predict disease progression, and recommend the most effective intervention, leading to more accurate diagnosis and optimized treatment outcomes. Second is improve medical imaging.
Machine learning algorithms excel at image recognition and analysis. In the field of medical imaging, machine learning can enhance the accuracy and efficiency of image interpretation, aiding in the detection of abnormalities, segmentation of organs or tissues, and even predicting disease outcomes. This can lead to faster and more accurate diagnosis, reducing the need for invasive procedures and improving patient care. And third is remote patient monitoring. Machine learning can contribute to the development of wearable device and remote monitoring systems. This device can continuously collect patient data such as vital signs, activity levels, and sleep patterns. Machine learning algorithms can analyze this data in real time, detecting anomalies, predicting health deterioration, and providing early warnings to healthcare providers. This enables proactive intervention, reduce hospital readmissions, and improve patient outcomes. And then lastly, fourth is drug discovery and development. Machine learning can significantly accelerate the drug discovery process by analyzing vast amounts of biological and chemical data. It can assist in identifying potential drug targets, predicting drug efficacy and toxicity, and optimizing drug formulations. By enabling more efficient and targeted drug development, machine learning has the potential to revolutionize the pharmaceutical industry and bring new therapies to market faster. So, in conclusion, machine learning has become a technology that is changing the healthcare industry. Its use in drug development, remote monitoring, therapy optimization, and diagnostic have the potential to revolutionize patient care. Machine learning algorithms can help medical personnel make more precise diagnoses, forecast outcomes, and after personalized therapies by analyzing vast volumes of data and spotting patterns. To preserve patient safety and confidence, it is crucial to solve issues with data privacy, regulatory compliance, and algorithm openness. Machine learning has significant promise for increasing healthcare delivery, enhancing patient outcomes, and fostering new horizons in medical innovation as it develops.